Hello, this is Jakub Staroń here on MedChem Essentials scientific seminars. Today we will continue talking about permeability with the focus on permeability optimization. To begin with, we need to introduce permeability influencing factors. Then we will discuss how transporters affect permeability and some practical example topped with a summary. So, what factors affect permeability? For sure, it's a charge, because of a pH partition hypothesis. It states that only the unionized form can cross the membrane. However, this is true only for passive permeability. On the figure here, you can see that pH in plasma is like 7.4. So, basic compound, majority of drugs are basic, will be unionized, mostly unionized in this environment. So it can cross the membrane, which is very lipophilic. So an ionized form cannot cross because it's very polar. Urine has pH is slightly acidic with pH of 5.4. So basic compound will be mostly ionized in this environment and cannot cross the lipophilic membrane. Let's have some example. Let's assume our drug has a piperazine in its structure. The drug is fairly polar and basic. It has very poor permeability. And we need to optimize it, increase it. If we methylate the nitrogen, the compound becomes much more lipophilic, slightly less basic, and already has some permeability. But still, it's not on the good side. If we strip the molecule out of all basicity by introduction of this electron withdrawing difluoroethyl group, the compound becomes much more lipophilic, non-basic, and already quite highly permeable. One remark, charged compounds can still be a substrate of active transport. So even though this uncharged can passively permeate the membrane, the charged compound can still be actively transported. Now, what other factors affect permeability? For sure, this is lipophilicity and size. What are the trends here? The trend is, if we plot the drugs across log D and permeability, we will see that generally with increase of lipophilicity, we will see increase of permeability. This is the general statistical tendency. Now size. If we have the same plot, and statistically, we will see that compounds with increased molecular weight will show lower permeability, generally. So, because the larger drugs, they have higher problems to actually squeeze through membrane or be actively transported. This is a general rule, of course. There are exceptions if a compound is a substrate of active transport. Now, let's move to the two transporters. We discussed on the previous MedChem Essentials that PGP is the most commonly expressed multi-drug efflux transporter. It favors specific groups. So it's not that it recognizes everything. It's very general, yes. It can actually pump out multiple different compounds, but it favors compounds especially with hydrogen bond donors. So compounds that will have moieties like primary, secondary amides, ureas, sulfonamides, alcohols, phenols, carboxylic acids, or heterocyclic groups with uncapped amine group, they may have higher chance of being a substrate of PGP efflux. We have some general guidelines for minimizing PGP recognition, and this will include maximize ligand efficiency. On ligand efficiency, we'll have a future talk. And keeping the hydrogen bond count below 2. These charts are from fantastic paper published, reproduced here on a nice figure that shows this is the efflux ratio, average efflux. Everything, as you know, everything above 2 is a substrate of PGP. Here is 2, here is 3. In this paper, 3 was taken as a reference for being a substrate of PGP. We have polar surface area, H-bond donors count, log P, H bond donors count for average A to B permeability. So to have a permeable compound that will not be a substrate of efflux transporters, we need to keep hydrogen bond donor count possibly below 2, polar surface area below 90, but preferably below 70. Let's move on to the practical example. This is a compound, our model compound. It's got some sulfonamide alcohol group, some amine group, and it's not permeable. We want to improve permeability of this compound. What we can do? For sure, we can remove NH or AH group by direct addition of different alkyl groups. This can be methyl, ethyl, anything that doesn't disrupt the biological activity. We can reposition the amide bond. This can actually hinder somehow the hydrogen bond donor, and we will lower the recognition by PGP efflux pump. We can cloak this NH group by positioning some hydrogen bond acceptors in the neighborhood. This can be either fluoride or, for example, a methoxy, for instance. So we'll form a kind of intramolecular hydrogen bond, and this will hinder again the hydrogen bond donor. This is needed in cases where the hydrogen bond donor is required for our biological activity. And finally, removing the basic group. But this we introduce on the first slide. So let's summarize our insights from this presentation. So the factors that affect permeability are lipophilicity, size, ionizability, and number of hydrogen bond donors. So to improve permeability, likely we need to increase log D, decrease size, exclude any ionizable group, and reduce number of hydrogen bond donors. Thank you very much for your attention. See you next time. Bye bye.